Hello everyone, welcome to the numerical methods class. In this class we will be at chapter 15, and in this chapter we will be learning about interpolation and specifically the Newton's polynomials. With the interpolation, our purpose is to fit a polynomial to a data which passes through all the points of the data. As you can see here, these different curves are passing through each point. So this is a little bit different from regression. In regression, we were trying to find the line or curve which passes through in between the data that predicts them in a middle way, let's say. But in interpolation, it's different. It's just passing through all the data. It has to pass through all the data while fitting a polynomial. So polynomial interpolation is determining the unique nth order polynomial that fits n+1 data points to estimate intermediate values between precise data points. So it has to pass through the data points that we have, and we can predict the intermediate points based on the polynomial that we fit into these points. An nth order polynomial can be defined as this, as you can see, with an increase of the power of the x's. X's are the data inputs, and fx is the output by multiplying of the coefficients with the data points to the power. And for n+1 data points, there is one and only one polynomial of order n that passes through all the points. So we need to have n+1 points to fit an nth order polynomial, and there is only one polynomial that passes through all the points. You can see here only one line for 2 points, only one line. For 3 points, a parabola at second order polynomial, only one, and a third order polynomial for 4 points only. And there are two mathematical formats of polynomials for interpolation that we are going to see in this course. First, Newton polynomials, then Lagrange polynomials. Especially in this chapter, chapter 15, we will be seeing the Newton's polynomials. Newton's polynomials are defined for an nth order polynomial type. You can see here the formulation. It has coefficients b0, b1 up to bn, and next to it we have a subtraction of the target input from the existing data one by one, starting from the zeroth data. So this can be the first data you can think of, and the next data, the other data, and these are the inputs actually. So for the first coefficient there is no multiplication, but for the second coefficient there is a multiplication of this subtraction of the unknown, the input which has the unknown output minus the data point, the first data point. Then it goes like this. For the nth coefficient, there is a multiplication of all the data points subtracted from the x values, you can see here. And the data points can be used to evaluate the coefficients b0 up to bn. And for an nth order polynomial, n+1 data points are needed. As you can see here, we need these x input data and outputs of them. We will have these data. By using these data, we can simply calculate the coefficients, which are b's here, using these functions. And these functions, actually, this is just the first function value of this value. But the second one, the third one, so you can see x0, x1, x0, x1, x2, it's increased that way in the function. We are using the data points here by adding them up for each coefficient up to the endpoint. And these f functions with brackets actually are the finite divided differences. So the bracketed functions are the finite divided differences, basically the derivatives. But we are using the estimation of the derivatives as the finite divided difference. So this is the first finite divided difference is this, fxi minus fxj divided by xi minus xj. And this is the second divided difference. And in the second one, we have this first one here, as well as here, but I and j and k. So it increases because we will have in the second, for example, for this, so between x1 minus x0 here and x2 minus x1 here. Sorry, and this one is here and this one is here, and xi minus xk is x0 and x2, for example. For for the third term, for B2. So it goes this way for Bn. We have again an nth finite divided difference here, and this is coming from the previous one, and the previous one is coming from the previous, so it goes up to here, and these are added here, and you can calculate the nth finite divided difference as well. With these, you can find these f values, then calculate b values by them. That's why by substituting these finite divided differences to the polynomial here, we can obtain the final formulation of the Newton's interpolation. It is fx0, which is b0, you can see, and x minus x0 is here, b1 is this, so we write all of them, and for bn we will have this f function over here, and these are written here, you can see. Of course, there is the second term they defined here as well with b2. So this is the function. By chopping from here, for instance, we can have a linear interpolation. If you chop off from here, remove the rest, then you will have a second order polynomial, etc. And you can fit them to the data by using this formulation. Let's see how do we do that in the next slide. In the Newton's polynomial, the finite divided differences are used. We said this in the previous slide, and this is our formulation we mentioned in the previous slide as well. And we said that the derivatives are obtained using the data of the finite divided differences from the previous coefficient. So for example, for these, we will use this coefficient. Actually, this is x1. Let's define with this for the second one, x2, x1, x0, we will use the function here, but not only with x1 and x0, also with x2 and x1, because we have that too. And we can have a recursive order of the finite divided differences, as you can see in this table. So we start with the functions, and the first finite divided differences are used simply between these, and then use these, and then use this. And for the second divided differences, use this first divided differences for x2, x1, x0, and for x2, x3, x2, x1, use these two. Then use these two for the third, and it goes this way. You can have further, if you have further data, x4, x3, for example, x4, x5, etc. Then you can find here x4, x3, x2, etc. And here for the third order, you will have the other ones as well. And you can use this order to be able to calculate all the finite divided differences. It is not necessary that the data points used in the polynomial be equally spaced, or that the abscissa values necessarily be in ascending order, but it is good to have this, but it's not necessary. So for any data you can implement this Newton's polynomial.